Hey, this is problem sheet 7, and I've got some model answers for you. Let's look at the first question. First question is basically you've been given a Butterworth low pass filter and the transfer function is given in S domain, and you need to translate this into a high pass filter with a cutoff frequency omega c. So it's a simple transformation that you need to do. So you write down the normalized Butterworth filter, because normalized means one here, and then you do a low pass to high pass transformation. That is, wherever S, you replace them by the cutoff frequency divided by S. So what will happen is, here for S, we are going to substitute omega c over S here and omega c over S, and then you simplify this one. When you simplify this S squared, this will be a squared, will come on the top, and that's your on the denominator. And this makes sure that if you rewrite them H1 j omega in the frequency domain, you will find j omega whole squared divided by omega c squared plus root 2 omega c j omega plus j omega whole squared. So naturally, when omega equals 0, that's your DC component. This function will be, this whole thing will be 0, because omega 0 means. That means when you plot your graph, the magnitude spectrum H1 j omega, it was at omega, it will start from here. So that's basically, I mean, a high pass filter will do this. So basically, the DC value is 0, so it's a high pass filter. So you can always check it and see whether the results that you have got, whether it is correct or not. Right, we move on to the next question. In this question, you've been given a specification that you got to design an analog band pass filter. So that means it's monotonic in the pass band and also stop band, right? That's the property of the Butterworth filter. Now the pass band is given as 0 to 2 kilohertz, at a 3 dB cutoff is 2 kilohertz, and transition band is 2 to 4, and the stop band attenuation is -10, starting at 4 kilohertz. So if you translate these three into a response, it will look like this, and that's kind of 0 dB. That position is 1 or 0 dB in terms of dB, and -3 dB cutoff cuts at 2 kilohertz. And stop band start, this is your transition band from there to there. The stop band is from here onwards. At 4 kilohertz, it says -10 dB, so you put in -10 dB here. Now we're going to design the filter. So we start with we start with the Butterworth filter, and omega c is the cutoff frequency. You divide the omega and have that one. Now what you do is you take 10 log on both sides, take 10 log on both sides. When you do that, 2 comes at the front, so it will be 20 log h omega, which is equal to 10 log of 1 is 0, 10 log of 1 is 0, minus of this 10 log, so that will be 10 log of that, which is 10 log of 1 is 0, so it's minus of that, so that's, and this one is given as 10 dB, because that's our design is 10 dB, so this position is 10 dB. So we put 10 dB here and -10 log, and that cancel, 1 and 1 cancel, you got 1 here, so therefore that much equal to 10 to the 1, which is 10, so you got that part now. Now you substitute the value. We know we've been given that the cutoff frequency is 2 kilohertz, so that's 2 kilohertz for that part. And we put in the 10 dB, -10 dB at 4 kilohertz. So this will become 4 kilohertz now. So if you simplify this, 10 goes on that side, that's be 9. This one will be 2. So if you take log on both sides, so you'll have 2 to the power of 2n is equal to 9. Therefore, 2n log 2 is equal to log 9. Therefore, n equal to log 9 divided by log 2 divided by 2, which is 1.6. So n become 1.6, so n equal to 2 will satisfy the requirement of this particular filter. So it's a second order Butterworth filter will satisfy this requirement or this frequency response. So we say therefore n equal to 2 will satisfy the requirement. That's your second part of your question. And the third part of the question says, show that the transfer function of the second order normalized Butterworth filter is this one. So you're going to show this is the normalized Butterworth filter, second order filter. So we start with the original Butterworth equation, which is in the notes. That's what the Butterworth equation is. The magnitude squared is equal to 1 plus omega to the power 2n. And magnitude squared we have learned can be written as hs times h minus s, we can write them as. And you multiply by j on the top and the j on the bottom, and you will get this one. And the j omega is replaced by s, and j is underneath. Now we will now find that if you make n even, this will j squared will become minus 1, and even means minus 1 times minus 1 is plus. So what you end up with is that one. So this will now come as that for n equal to even. So this is hs squared. So the hs will be, you take the square root of this one, and that's your transfer function. And it's explained in the notes how we get this one. And you basically take the left hand side of the pole, and this is what you get. Or you can go back here again and you substitute this j omega, and this will be hs squared, this will be hs. Well, it's better to not to do the magnitude, but it's hs squared. From that you can find hs as well. So it doesn't matter. All you need to do from the magnitude, you convert this, and then you get this part. Once you have got that, now you got to start to work on it. So we go to, these are the poles. Poles mean that part has to be 0. So you go consider the poles. So 1 plus s2n equals 0. That means s to the power 2n equal to minus 1. So minus 1 mean in our exponential form e to the power j, which will be cos j pi. It will be cos pi plus j sine pi. Cos pi is minus 1. So we would have e to the power j pi here. Plus and minus satisfies that. So you got both. Plus you add 2k pi to get all the solutions. So now you would have s is equal to, so you divide that by 2n, you get your s. So s is, that's your poles. Now we know we are only looking for a second order pole. That's what the question was. So all we need to do is we substitute for k equals 0, k equal to 1, will give you the required poles. When you substitute k equals 0, you get j pi over 4, that's the first one, and n equal to 2, remember? And then k is equal to 1, you get that. Now what you do is you plot on the s-plane all these poles. That's plus or minus, plus or minus. So one is here, another one is there, other one is pi over 4 here, minus pi over 4. This is 3 pi over 4, minus 3 pi. These are all poles. Sorry, even though I just put a square, that's all poles. For stability, all we need to take is the poles on the left hand side. That's all we need. So you read them. You don't need the right hand side. The reason you get both is because we started with hs, h minus s. hs is this side, h minus s is that side. You're only interested in hs, so you only read this side of the poles, which is now, this is pi over 4. So you need to find that value and that value to write the pole. That will be, so we can say this is S1, this is S2. So that's the equation. Now S1 is equal to S minus, this is minus 1 over root 2 plus J 1 over root 2, because this is 45 degrees, this is unit circle. Similarly, this will be minus 1 over root 2, also minus 1 over root 2 there, minus 1 over 2, J minus 1 over 2. If you simplify, if you multiply them out, that's what you get. That's your second order filter. This is just a simple example of how do you find the transfer function of a Butterworth second order filter. So you start with the Butterworth magnitude function and work your way through. So this is even number. If it's odd number, you will have a minus here, and then you can redo the calculation again. So it depends on the odd or even, you could choose the appropriate transfer function Hs. Again, it's explained in the notes, you could have a quick look at that. Now we go to question 2, second question. In this question, you've been given, again you find the low pass Butterworth filter, and cutoff frequency is 500 Hertz, stop band is 1 kilohertz, this is 40 dB. So it's not a difficult question, same principle. First we need to find the order. So we go here, start with the same principle as we did in the previous question. Take 10 log on both sides. When you do that, this will become, that's equal to that. And then this is given as minus 40 dB here. So you put minus 40 dB, minus 10 that. So you will get, this and this cancel will give you 4. Then when you remove the log, that will be equal to 10 to the 4. So you will have that. Now bring this one to that side, and then you find 2n, which is taking the log. So if you do the 2n, you get log 9999 divided by log 2. And from that, you will find, you need to substitute omega c is 500 Hertz and omega is 1 kilohertz, as we did before, correct? And then you get 2n is equal to this over this, and which give you 13. Therefore, if you divide that by 2, you will get n equal to 7. Now when you divide this 1000 over 500, you get 2, and that's the 2 coming here as a log 2 there. So it's n equals 7. Now in this case you see it's an odd number. So how do we calculate the pole position? So first we calculate the omega c, because 500 Hertz, omega c is 2 pi 500 Hertz, that's 1000 radians. Now we start again. That's your Butterworth filter magnitude function, and you rewrite multiply by j and j here, you rewrite the function that way. And then you say this must be equal to 0 to find the pole. So you say that must be equal to 0, which means that's the power 14 because it's 2n, n is 7. 14 equal to minus 1. So that means, so slightly differently I'm doing here compared to the lecture notes. So same principle. I just did not simplify this. I didn't bring, in the lecture note I would have brought this up as j here, and then I would have put a minus sign there. Instead of that, I kept the j here. So from here, I can say this is e to the power of j pi. And then to find this one on its own, it's e to the power j pi plus 2 pi k divided by 14 is your pole. Now what we do is you cross multiply this one to find this. You cross multiply, so you get j and 2 pi c. We know j is equal to e to the power of j pi over 2, right? We have learned that before. So you now substitute for j as e to the j pi over 2. And then you write this bit plus that, right? Those two. And you will find that's your pole position. So what does that mean? We need to have altogether 7 values, n equals 7. So we put k equal to, we have already used 7. So 7th order filter we need. That means n equals 0, k equals 0, 1, 2, 3, 4, 5, up to 6. So you substitute value for k. By doing that, you will get the pole positions as k equal to omega c, which you already calculated, 1000 pi, times this. Now you substitute k equal to 0, 1, 2, 6 on this equation here. As soon as you do that, you get the first pole, k equals to first one, second one, third one, fourth one, and so on. You get all the pole position. So that's another way of doing it. The reason I'm doing this question is that similar one is done in the lecture notes as well, but I just wanted to do it this particular way and bring in this one and multiply my j pi over 2. So you can redo this question again yourself and see whether you understand. We move on to the next question. Find the order of the Butterworth filter here also. Given the cutoff frequency is so much radians per second, amplitude response is 20 dB down and omega is equal to 3 radians per second. So we've been given that the cutoff frequency omega c is there, and then is 20 dB down when your omega s is going to be at 3. Well, even though we call this is 3 radians per second, and this one is 0.75 rad per second. That's your graph. Start with our normal equation. That's the equation for us, and then take 10 log on both sides. And now you substitute 10 log. When you do this, this is 0, so that part is there. This 10 log now become minus 20 dB at omega equal to 3. So you put minus 20 dB and put omega equal to 3 there. And cutoff frequency is 0.75. Substitute that as well. Now you do the simplification as we have done before. From here you get 2, and then you simplify. I don't need to go through this simplification again. And you calculate the n become 1.657. Therefore, n equal 2 will satisfy the requirements. So different questions, different ways you've been given, and you really have to work out, you know. And there's not much a difference between this question and the previous questions, you know. So the principle is same. Question 4. Consider a Butterworth low-pass filter, n equal to 5 and the cutoff frequency omega c equal to 1. Find the two end poles, hs, h minus s. Determine hs. Find the transfer function corresponding to the high-pass filter with the cutoff frequency. So it's the Butterworth filter order is given to you. So low-pass filter of order 5 is given. So 2n will be 10 poles altogether. So 5 on this side, 5 on that side. And this will be uniformly distributed around the unit circle in the S plate with the angular spacing of pi over 5. So you will have altogether 10 positions. As I said, there are 2n is 10. So you go angular spacing of pi over 5. So it's 2 pi is the whole thing, divided by 10 will give you pi over 5. So you start with this. Your first position is there, first pole, and you pi over 5, 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 and there's another one, pi over 5, pi over 5, and so on. Now only you need to read, you need to find hs. This is h minus s, you can see that. All you need to read that value corresponding to the complex one, that one, and that one. That's all you need to write your transfer function. So we can write the transfer function. We start with the first one as this one, which is minus 1. This is minus 1. So s plus 1 will be the first one. And the second one is this one and this one. If you look at that much, it is 4 pi over 5. That matches. This is 4 pi over 5. This is 4 pi over 5. So you can say that is s plus cos 4 pi over 5 plus j sine 4 pi over 5. Then you go for this one, that one is 3 pi over 5. So it will be cos 4 pi over 5 minus this. It should be, they all should be, like when you write that thing, s minus s1. So first one is s minus of minus 1, which is giving you s plus 1. Similarly, the next one is s minus s2. So you got to find you got to find this value and the value, and they one is negative, one is positive. One is negative, that's why you get the positive sign here, and then other one is positive, and then when you subtract that will be positive as well. So if these two are positive, and then conjugate will be negative. And then if these two are positive, conjugate will be negative. Anyway, you can work this out, writing down. And when you simplify them, that is your HS. That's a very straightforward question, that one is. And if you look at the next part, it's even straightforward. So this is your cutoff frequency. So what you need a high pass filter, similar to the first question we did. So if you multiply all of these, you will find, because that's 1, that's 1, that's 1, the whole thing will be, the last term will be 1. So you do a low pass to high pass transformation, you substitute S by SO omega C, same thing as we did here, and substitute everywhere here and here, and then you simplify. That's your filter that you'll get. This is low pass to high pass transformation. We did this here. You can see that in this is only denormalization. So what we should have done is, this is not correct actually. What we should have done is low pass to high pass transformation is S is replaced by omega C over S. That's what we should be doing. This is only a denormalized transfer function. This will not give you a high pass filter. So if you really want a high pass filter, what you need to do is wherever S here, you go back here, HS equal to 1 over, S should be replaced by omega C over S plus 1, first one is times omega C over S whole squared plus 6.61 8 omega C over S plus 1. So that's your first one, and similarly the next one, and that's the one will then bring you S squared on the top, or S to the 5 on the top, and that's then become as a high pass filter. There must be an error in this question, whether it's a denormalization or high pass filter. If it's a high pass filter, this is what you're going to do. That's purely for denormalization you're doing it. This is the only one which will change the filter. This will not change the filter characteristics. All you're doing is you're scaling it. Whereas this one will change the filter characteristics. The low pass filter will become high pass filter. So make the change in the solution. If this is what is there, this is purely for denormalized transfer function. You need to really do this substitution to get the low pass to high pass transformation, similar to the question that we did, question number 1. That's exactly what you need to do here. Okay. Now the last question, I think this one is here. A first order low pass prototype is to be transferred to a band stop filter. So far we did low pass to high pass. Now we are going low pass to band stop. And the mid band rejection frequency is omega naught. And you need to do a transformation and find the transfer function of the band stop filter. HS at S equals 0, you're going to find S infinity, and that also you've been asked to find. So low pass to band pass transformation has to be given to you. It's given. That's your transformation. And where B is the bandwidth, omega naught the mid band rejection frequency. That's kind of a center frequency. That's what we're saying. So what we need to do is we start with the first order low pass filter. Right? We got the first order low pass filter. This is your transformation to bring a band stop filter. So you just substitute wherever you have in the first order low pass filter, instead of S, you put in Bs over S naught omega squared plus 1. Now you simplify this, you get that's your transfer function. That's your low pass to band pass transfer function. It's a very straightforward transformation that you've been given. The transformation is anything between low pass to high pass to low pass, you need to remember that. That's a very simple one. But anything above that, like band stop band pass filter transformation, you will be given, because there are varieties of them available. You cannot remember all of them. So you will be given a transformation like that, and then you substitute. So now you got this one. So this is your band stop filter now. Once you have got it, you need to find what's the gain at s equals 0. What does that give you? S equals 0, you will find s is equal to 1. So what we are saying is h naught is equal to 1. Okay? And then what's s infinity? So s infinity, how do you find s infinity? You look at these two are same powers. You would have done that this in maths. So you divide by s squared up and down. So when you do the division by s squared, you'll get 1 plus omega naught squared s squared, 1 plus b over s, that over s. If you now substitute infinity, this will go to 0, because omega naught squared over s squared, when you substitute infinity, go to 0, because this is large value on the bottom. Similarly, that goes to 0, that goes to 0, you end up with 1 and 1. So h infinity also roughly 1. Yep, almost 1. Then they ask you, what is h j omega on the axis? On the axis, at the center frequency, the value is 0. When you substitute that directly, you get, because as soon as you put j omega naught whole squared, this will become minus, and this cancels with that, you get 0. So how does that look like? So if you really now draw the graph, that's omega, that's, we call it h1 omega. So at omega equals 0 is 1, 1. Omega infinity, I just take that position or something like that. That's also 1. Yeah, it should be infinity means far away. But omega naught, say let's that position omega naught, j omega naught, that's 0. So graph is 0. So what happens is this graph comes down like that, sharp up, so goes all the way like that to 1. So it's a very narrow band stop filter. It stops that frequency. It's like a notch filter. This is like a notch filter, basically. It's take out that omega naught component. So it could be a 50 hertz frequency that is annoying you in your signals, and you want to remove that. So you use this filter. That filter will take it out in the analog domain. This is for analog filters. So that's just the graph, and it is a band stop filter. Clearly from that, these three values, you can actually show it as a band stop filter. I think that's all chapter 7 filter design, analog filter design. I think mainly we have been concentrating on Butterworth filter, and using Butterworth filter we can do transformation to get all the other type of filters. Okay? So if you concentrate and redo these questions and questions on the notes, and I think you'll have a good idea of how to design Butterworth based filter, and then how to do transformations. And the last part is very multiple choice question type. Elliptic filter has ripple in the passband only? No, that's not correct. No ripples in any of the band. That's Butterworth filter is the only one. Ripples in both bands, that's definitely elliptic filter. None of the above, that's not true either. Ripple in passband is, you've got Chebyshev filters, Chebyshev 1 and 2 type, and so basically this would be the right answer. But let's look at elliptic filter has got other thing as well. It has got minimum transition band, which we didn't put it in here at all. But ripple in both passband and stop band. So if you look at the elliptic filter, it has got ripple in passband and ripples in the stop band, and that distance is minimum compared to other filters. You can design 20th order Chebyshev filter, Butterworth filter, and elliptic filter, same specification. And when you finish the design, you go and measure the transition band. This is the one which will has the minimal transition bandwidth compared to the other. So minimal transition bandwidth is very good because the filter is going to be very sharp, very quick, So that's just to give you an idea of just characteristics of elliptic filter. So you just have to tick that one is the answer for that. Understood? Okay. All right, that's all for you in that chapter, and thank you, and try all these questions. You should have no problem then able to tackle any questions.